Mass Aspirants groups organizes online problem solving sessions to help the students who prepare for different national level competitive examinations like IIT, JAM, CSAR, NET, GATE examination, NBHM exam, etc. As a part of that ongoing series, today we have Ms. Dipali Anup Savant, Assistant Professor, Department of Mathematics and Statistics, GN Khalsa College, Mumbai, is with us to engage a session on functions of several variables. She will discuss with you selected problems from that particular area, functions of several variables, which is in the syllabus of both IIT, JAM, GATE, and NET exams. So I'm sure that today's session will be really helpful in your preparations for these exams. I would like to express my sincere thanks to Ms. Dipali for inviting our invitation and joining with us. I welcome everyone to this program. Welcome, Dipali.
Thank you for the warm welcome. I'm going to talk about functions of several variables, particularly the limit, continuity, and the derivative part of it. As Sir has rightly mentioned, my main emphasis will be on the problems which appears in the JAM examination. So I will be mainly talking about the functions of, when it comes to functions of several variables, I will be mainly concentrating on scalar valued function. There are two fundamental results which I want to discuss here, which will be useful in the future. So I'm going to pick up two results over here. The first result talk about the limiting value of sine 1 by x, which does not exist, because if I take x is equal to 1 upon pi by 2 plus 2 pi n. Okay, so as n goes to infinity, x goes to 0, and the value of sine 1 by x for x of this type turns out to be 1. Whereas if I take x is equal to 1 upon 3 pi by 2 plus 2 pi n, as n goes to infinity, x goes to 0, and we can see the value of sine 1 by x for these kind of x turns out to be -1. The limit is not unique, and hence I can conclude that the limiting value x going to 0, sine 1 by x does not exist. Now let me define a function f of x is equal to x into sine 1 by x when x is not equal to 0, and 0 when x is equal to 0. So it can be checked since sine 1 by x, it is a bounded function. Okay, we can check on our own that this function is continuous at 0. So if I'm looking at limit x going to 0 mod fx minus f of 0, this will be limit x going to 0. Observe that this value is non-negative, so it is greater than or equal to 0. So this will simply turn out to be x into sine 1 by x minus 0, which is equal to limit of mod x sine 1 by x. And since mod of sine theta is less than or equal to 1, this will turn out to be less than or equal to mod x, which is equal to 0. So as we can see here, the term mod fx minus f0, the limiting value of mod fx minus f0 is sandwiched between two zeros. Therefore, I can conclude that limit x going to 0, f of x is equal to f of 0, leading to the result that this function is continuous. Whereas this is not differentiable, because if I take the limit representing the derivative, if I'm looking at f dash of 0, it is simply limit x approaching 0, fx minus f of 0 upon x minus 0. On substituting the values and simplifying, you will observe that this is x into sine 1 by x divided by x, and hence it is limit x going to 0 sine 1 by x, and I have already proved that this particular function or this particular limit does not exist. Okay, this does not exist. Now let us try to explore some more. So if I take fx is equal to x raised to n into sine 1 by x for x not equal to 0, and I'm doing this for n bigger than or equal to 2 and 0 when x is equal to 0, then this function is continuous as well as differentiable. One can prove this by using the argument which I have discussed up. Now from here, this will be a result which will be used in many of the problems which we will be doing ahead. Now let me switch to my original topic. I'm going to talk about the limit. Initially, we'll discuss the limit of a function, particularly a scalar valued function, and then we'll put this result into a vector valued function. So I hope we all know that a scalar valued function, it is a function, a scalar valued function in general is a function f from S, which is a subset of Rn to R, where S is non-empty. Okay, this is called a scalar valued function. Vector valued function, the codomain is going to be Rn. Okay, I'm not getting into the formal definitions of these two functions. Anyway, they will appear in the definitions which I'm going to do ahead. But just to give you a brief idea about the difference between scalar valued and vector valued function, I thought I will brief you this. Okay, so going ahead with this, let S is a subset of Rn. It's a non-empty open subset of Rn, and f from S to R be a scalar field. Scalar field, scalar valued function will be treated equally in my session. Let A is an element of S and L is some finite real number. Then I can say that limit x approaching A, f of x is equal to L. It is good to see the epsilon delta definition in the beginning. If for epsilon positive, there exists delta greater than 0 such that if 0 is less than norm x minus a less than delta, implies then mod of f of x minus L is less than epsilon. Now here when I'm referring to a norm, I'm referring to a Euclidean norm, which is nothing but norm of x is equal to under root x1 square plus x2 square plus xn square. Okay, let us see an application of epsilon delta definition here. So I have taken a function f of x given from R2 to R, defined as fx is equal to x into sine 1 by x plus y into cos 1 by x, when the product x and y is non-zero and 0 otherwise. What I have to do is I have to check if the limit x y going to 0, 0, f of x exists or not. My claim is that the limit exists and the value is 0. Okay, and as I said, the tool which will be used for proving this will be an epsilon delta definition. So let us start with some epsilon positive. In order to prove my claim, I should be able to find delta greater than 0 such that whenever mod of x minus y, sorry, x comma y minus 0 is less than delta, fx minus 0 should be less than epsilon. Okay. Now norm of f x comma y minus 0 comma 0 is simply under root x square plus y square. I have to evaluate delta. Suppose this is less than delta. Okay. If I'm able to find the value of delta, I'm done. The delta value in terms of epsilon. Okay, so consider mod of fx. So I have a function f from R2 to R given by f of x comma y is equal to x sine 1 by x plus y cos 1 by x when x into y is non-zero and 0 otherwise. Now I need to find the limiting value of f of x at 0, 0. Okay. My claim is the limiting value of f of x comma y when xy approaches to 0 is 0. We will be taking the help of epsilon delta definition. So let epsilon be positive. My aim is to find delta greater than 0. Delta will be expressed in terms of epsilon later on, such that when 0 is less than norm of x comma y minus 0, 0, when it is less than delta, then mod of fx minus 0 should be less than epsilon. Okay. So suppose norm of x comma y minus 0, 0, which is nothing but under root of x square plus y square is less than delta, where delta is to be determined. Okay. Consider mod of x f of x comma y minus 0. Substitute the value. This will turn out to be mod of x into sine 1 by y plus y into cos 1 by x. Right? By triangular inequality, this will be less than or equal to mod x into sine 1 by y plus mod y into cos 1 by x. And now we know that sine and cos, they are bounded functions. So mod of sine x and mod of cos x both are less than or equal to 1. So this equation will be further less than or equal to mod x plus mod y. Mod of x is nothing but under root of x square. Mod of y can be written as under root of y square. Each of these terms will be further less than or equal to under root x square plus y square, which is nothing but 2 times of under root x square plus y square. Now observe that this is precisely your norm of x comma y minus 0 comma 0. And I have mentioned over here, I'm taking this value to be less than delta, which I'm supposed to be valued. So this is less than 2 delta. And further, this will be less than epsilon if and only if I take my value of delta is equal to epsilon by 2. Okay, so hence for delta equal to epsilon by 2, which is positive. If I take norm of x comma y minus 0 comma 0 less than delta, mod of f of x comma y minus 0 is less than epsilon. So I can conclude that f of x comma y, when x comma y approaches to 0 comma 0, the limiting value is 0. So this example just gives me how to apply the epsilon delta definition in this particular example. Now there is a result which talk about the uniqueness of the limit. If the limit of a scalar value function exists, then it is unique. Okay. Now, when I'm talking about the uniqueness of the limit, okay, when x comma y approaches to the point a comma a, the value should be the value of the limit should be unique along all the possible paths approaching the point a. So here, this result can be used in a contrapositive. So if the limit is not unique, the limit doesn't exist. So here is one good example. I have f of x comma y is equal to x square minus y square upon x square plus y square if x comma y is non-zero and 0 otherwise. I want to check if the limit of this function exists at the point 0 comma 0. Consider the limit f of x comma y when x y approaching to 0. Now, what I observe over here is, I can see that the powers of x and y are equal. So, let us take the limit along the path y equal to mx. So, if I replace y equal to mx, this function can be totally expressed in terms of x squared. There's a mistake over here. It is m squared into x squared. I hope you will consider this. You do not have a, I don't know. There is no option of a pen over here. Maybe I'll do that later. Okay, so I have x square minus n square into x square. Please read this as x square plus x square, sorry, upon x square plus n square x square. You can apply the cancellation on x square because x is approaching 0. That doesn't mean x, that therefore x is non-zero. On applying the cancellation, I can see the limit expressed in terms of m, but m is arbitrary real number. And the limit depends on m. So as the value of m changes, the limit changes. That means the limit is not unique and hence it does not exist. Okay. Going to my next example. Okay. Now there is one page which was missing over here, but then the definition of continuity, maybe I should write it over here. So once again, I have a scalar valued function. So I can say a scalar valued function f of x is said to be continuous at x equal to a if limit x approaching a, f of x is equal to f of a. Right, now keeping this in mind, I want to find the value of alpha so that the function is continuous. Okay, so I have f of x is equal to x into x square minus y square upon x square plus y square if f of x comma y is non-zero, and alpha if f of x comma y is 0 comma 0. Okay, so basically the function will be continuous if the value of alpha is the limiting, value of the function. So consider limit x comma y approaching 0 comma 0. f of x comma y when x is not equal to 0, which is x into x square minus y square upon x square plus y square. Now, to find the value of this, I can also take help of a polar coordinate. So instead of using Cartesian coordinate, let me take x is equal to r cos theta, y is equal to r sin theta. So when I simplify this, so as x comma y go to 0 comma 0, r, which is under root of x square plus y square, goes to 0. So this is r cos theta into r square cos square theta minus r square sin square theta divided by r. On simplifying this, you simply get r into cos theta into cos square theta minus sin square theta, and the limiting value turns out to be 0. So if I take alpha is equal to 0, then my function turns out to be continuous. So this is one of the good applications wherein you can use the polar coordinate to handle the question of continuity. Okay, now switching to my next topic, limit and continuity of a vector value function. Okay, so I have already told what is a vector value function. So let f be a function from Rn to Rm given by f of x is equal to f1x into f2x into fmx. Now this is a vector value function. Now each fi from Rn to R is a scalar value function. This is also called a component function of a vector value function. Okay, let us discuss the limit of a vector value function. So let S be a subset of Rn. It's a non-empty subset of Rn, and f from S to Rn be a vector value function. Let me take A is a point of the domain S. An element L of Rn, that is, I'm taking a vector from Rm, that is L, is said to be a limit of f of x at x equal to A. That is, limit x approaching A, f of x will be equal to L. Once again, the epsilon delta definition. For epsilon positive, there exists delta greater than 0, such that whenever x minus A is greater than 0 but less than delta, norm of fx minus L is less than epsilon. Okay. Now here there is a result one result which will help me to use the limit part of a scalar value function to a vector value function. So suppose the vector value function mentioned in the above definition, which is of the form f1x, f2x, fmx, and my limit L is equal to L1, L2, Lm, as this is a vector from Rn. So I can say the limiting value of f of x is L if the limiting value of the ith component is Li. Okay, so limiting value of fx is L if the limiting value of fix is equal to Li. Now let us see how does it help me to solve the problem ahead. Okay, so here is one example. So I have a function f from R2 to R3 given by f of x comma y is equal to x square comma y square comma x square. Okay, so I want to know how to find the limiting value of f of x comma y at 0 comma 0. So it is a limit x comma y. So as you can see, your first component function is x square, the second component function is y square, the third component function is x square. So what you have to do is you have to just evaluate these limit of these functions at 0 comma 0. So find limit of x comma y approaching 0 comma 0 x square, which turns out to be 0. Limit x comma y approaching 0 comma 0 y square turns out to be 0. And limit x comma y approaching 0 comma 0 xy also turns out to be 0. And that's how you can evaluate the limit of a vector value function. Jumping to the continuity, let S is a subset of Rn, be a non-empty set, and S is a f is a function from, there is a mistake over here, f is a function from S to Rn. Then f is said to be continuous at A if the limit x approaching A, f of x is equal to f of A. Okay, I will not get into the epsilon delta definition of proving continuity, but there are various. Let us take help of the scalar valued function. So here is one very nice result which says for the f given in the above definition, I can say f of x f of x, which is of the form f1x, f2x, fmx, where each component function fix is a function from S to R, where I varies from 1 to m. F of x is continuous at x equal to a if fix is also continuous at x equal to a from I varying from 1 to m. Over here you have m because there are m components. Okay, so let us understand this through an example. I have f of x comma y comma z given by zx plus z, 6xy plus 2, 4xy comma 4xyz, and I'm checking the continuity at the point 1 comma 1 comma 1, right? So now you can find the value of f of 1 comma 1 comma 1, but let us check the continuity of each of the component function. I'm taking the first component function as f1, which is zx plus z. When I evaluate the limit of f1 at zx plus z, it turns out to be 2, whereas f1 at 1 comma 1 comma 1 is also 2. So f1 is continuous at 1 comma 1 comma 1. Similarly, you can check the continuity of f2, which is 6xy plus 2, and f3, which is 4xyz, and you will find that both of them are also continuous at 1 comma 1 comma 1, and that's why the vector valued function f of x comma y comma z is also continuous at 1 comma 1 comma 1. Okay, now try proving this exercise on your own. Okay, we all know that mod x is a continuous function at 0, right? So mod of x plus y is also continuous at 0 comma 0, and x into y is also continuous function at 0 comma 0. You can prove that each of them are continuous at 0 comma 0, and hence the vector valued function f becomes continuous at 0 comma 0. Okay, now this is something interesting. This linear transform plays an important role in the derivative of a scalar valued function and vector valued function. Linear, fine. So T is a linear transformation from Rn to Rm. Then I just missed out one page in the previous slide, but the page says very clearly that every linear transform, which is a scalar valued function, is always continuous. Okay, checking the continuity is not difficult, but right now we'll assume the result and go ahead. I missed out the result over there, so I'm mentioning the result over here. So T is a linear transformation from Rn to Rm. Then T will be of the form, since it is a vector valued function, it will have the component functions T1, T2, Tn. Okay, so each linear transform, which is a scalar valued function, is continuous. So each Ti is a continuous function leading to the capital T over here, also continuous. So every linear transformation is a continuous function. Now there is something what I wanted to note over here. Every linear transform from Rn to Rm is of the form Tx is equal to Ex. So I have where A is a matrix of order m cross n. In the linear algebra, we have seen how to evaluate this particular matrix. And we know that every map of the type Ax is nothing but a linear transformation. So they are continuous map. This will be useful in future. So let us keep this result in our mind and proceed ahead. Okay, now we'll go ahead to the important part of this discussion, that is directional derivatives. Okay, so directional derivatives are basically the rate of change of a function at a point in particular direction. That is a definition or the common understanding what we have. Let us see what is the definition. So I have a function, again, I'm talking about a directional derivative for the scalar valued function. These concepts can be extended to a vector valued function, and we'll see that afterward towards the end of this session. So let f be a function from S, which is a subset of R, and of course S is non-empty, to R. So I'm having a scalar valued function over here. A is a point in S. Use the unit vector in Rm, that is from the domain. Then the directional derivative of f at x in the direction of u is given by, it is denoted by the notation du f at a, and it is nothing but limit t approaching 0, f of a plus u minus f of a divided by. Let us understand the definition with the help of an example. So I have f from R to R given by f of x comma y equal to x square plus 2xy. I want to calculate the directional derivative of f at point A, which is 0, 0, in the direction of u, which is a vector 1 by root 2, minus 1 by root 2. Now, I need to check whether u is a unit vector. So, calculate the norm. Okay, the norm is given by under root x coordinate square plus y coordinate square. So, if you simplify this, you will see that the norm is 1. Okay. So, u, what I see over here is a unit vector. Now, let us apply the definition here. du f at A will be given by limit t approaching 0, f of A plus tu minus f of A. Now, A is 0, 0. So, this is f of 0, 0. A plus tu simply turns out to be A is 0, u is half, minus, 1 by root 2, minus 1 by root 2. So, this A plus tu turns out to be t upon under root 2, minus t upon under root 2. Substituting the value of the function, substituting this particular vector in the function, you get t square by 2 minus 2t square by 2, which turns out to be minus, on solving this, you get minus t by 2, which turns out to be 0. And that is how you calculate the directional derivative. Okay. Now, as an exercise, try calculating the directional derivative for function f of x comma y at x square, f of x comma y, which is x square plus y square plus x square
Ma'am,
plus y. Hello, yeah.
can you explain that portion once more?
This directional derivative concept.
Yes.
Okay, I'm just using a definition. So here is the function. Maybe I should do one thing. Let me just copy this. Give me a minute. Okay, so this is a function. You have to just follow the definition of a directional derivative. Okay, so I have, so if I'm looking at du f at A, by definition it is limit t approaching 0 f of A plus tu. A is a point where you are going to calculate a directional derivative. U is a vector along which you are going to calculate the directional derivative divided by t. Okay, so if you want, you can calculate these parameters separately. So f of A is f of 0, 0. You substitute the value where x is equal to 0, y is equal to 0, and you will observe that this is simply 0. You calculate A plus tu, your A is 0, t times your u is 1 by root 2 minus 1 by root 2. Okay, so this will turn out to be t upon root 2 minus t upon root 2. Evaluate your function at e plus tu. Okay, your function is x square
Yes,
plus
ma'am.
2xy. Okay, so substitute the value and then you will have the answer better. Right, it is 2 times minus t by root 2 comma t by root 2, and you simplify, you should get the answer. Okay, do you want me to complete the solution, or you can follow from here onwards? Shall I complete the solution, or it can be followed from this point onwards? I think from there it is easy to clear. Yeah, it is easy to follow from there, right? So now what I want you all to do is, whenever when I'll share my notes, you should try these kind of example. Okay. Now, looking
Ma'am,
at this example,
ma'am,
yes, Peter. Yeah.
ma'am, I have a doubt. In the definition
Yes.
of directional derivative, why you are changing to unit vector? In the vector direction itself, why you are not? We are converting to unit vector. Why? The
Okay.
definition.
So the vector what I have taken here, no, that is a unit vector only. That's what I said in the beginning.
Yes, Miss Ma'am. Why you are why you are converting to unit vector? In the definition itself, why you are giving unit vector? In the direction of the vector itself, we can t in plus t into u itself. We can. Why you are particularly to unit vector you are doing? Like,
Mostly unit vector concept is taken to get the uniqueness of the answer. If you don't take the unit vector, just imagine better. Like for example, if you take a vector u, how many vectors can you find in the direction of u? For example, I take a vector 1, 0. How many vectors can you plot in the direction of 1, 0? There are an infinitely many, no? Any vector along the direction of
yes.
x-axis, there are infinitely many answers. Now, when you are talking in the concept like derivatives, which are associated to limit, okay, we have a result which says that if the limit exists, then it is unique. And now, if I don't take a unit vector, how many values of directional derivative am I going to get? There will be infinitely
Yes,
many
ma'am.
values, right? So to avoid the redundancy or to obtain the unique value, we can have a unit vector. I hope that answers your query.
Oh, okay, ma'am. Okay. Thank you.
Yeah. So now we'll take the second example over here. So as our friend has asked us correctly, why we need a unit vector. And so I have another question over here. I have a function f of x comma y given by x square plus y square plus xy plus y. And I'm going to calculate the directional derivative of this at a point u in the direction of, at a point a in the direction of u. My point a is 1, 2, and u is a unit vector in the direction of 3, -5. Now, I never said u is a vector. U is a vector 3, -5. I said it's a unit vector in the direction of 3, -5. So observe that 3, -5 is not a unit vector. You can take the modulus of this, which is under root of 3 square plus -5 square, which is not equal to 1. So if I take v as this vector, u, which is v upon norm u, becomes the unit vector in the direction of v. So this will be the u which will be used in the definition of directional derivative. Okay. So try doing this exercise. Normally, you get the questions where your unit of the vector along which you have to calculate the directional derivative is not given to be a unit vector. So in that case, you have to do the changes accordingly. Okay. Now, one of the particular case of a directional derivative is when I talk about the directional derivative in the direction of the standard basis of Rn. Okay. So if I'm talking about R2, if I'm taking a directional derivative in the direction of x-axis or y-axis, or suppose I'm talking in terms of R3, if I'm taking a directional derivative in terms with respect to x-axis, y-axis, z-axis, that is in the direction of E1, A2, A3, then those directional derivatives are called the partial derivatives. Now, these partial derivatives play an important role in defining the derivative of the scalar valued function or a vector valued function. Let us understand what are the partial derivatives. So, I have a function f from, again, S is a subset of Rn, from there to R. A is a point in S. Particularly, we choose an interior point. That means A is not a found point on the boundary. Most of the time, they choose S as an open set. That is a set without a boundary. So A will be, since A is an element of S, which is a subset of Rn, A will be of the form A1, A2, An. Then the partial derivative of f of x at x equal to A with respect to the variable xi is given by the notation which is used over here is dou f upon dou xi at A, and it stands for limit h approaching 0, f of A plus hi minus hei minus f of A upon h. Okay. Now, if I evaluate this f of A plus hei, so what I will see is this number is nothing. This is nothing but a vector A1, A2. In ai, an increment h will be added, comma an minus a1, a2, an divided by h. So this will be a partial derivative of the function f with respect to xi at the point a, provided the limit exists. Okay. Now, okay. Now, however, this is one way of defining this. Let me just take an example over here. thought I will avoid the basic definition, basic example, but I can take one simple example over here. So as an example, I have my f of x comma y is given by x square plus y square, and my aim is I want to calculate dou f by dou x, that is the partial derivative of f with respect to x at 0, 0, and partial derivative of f with respect to y at 0, 0. Okay, so let us understand how the definition is applicable in this case. So derivative of f with respect to x at 0, 0 will be simply limit h approaching 0 f of 0, 0 plus h comma 0, or maybe you can say this will be little lengthy, but maybe after one or two example, I have not seen any of the student writing in such a detail, upon f of 0, 0 divided by h. So this will simply turn out to be limit h going to 0. If you simplify the bracket here, this will turn out to be f of h comma 0 minus f of 0 comma 0 divided by h. And now you can substitute the value of the function. Your function is x square plus y square. So put the values of x and y in each term. So in this term, the value of x is h and the value of y is 0. So this will be x square plus 0 square minus 0 square plus 0 square, which is precisely 0 divided by h. So it is simply
Ma'am, screen is not visible.
not
It's
visible.
stuck in before itself. It's stuck before.
Oh, give me a minute. I will share it once again. Okay, can you see now?
Yes, ma'am.
Okay, thank you. So I was discussing the example of how to calculate the partial derivative at a point by using a definition of a partial derivative. So I have a function f of x comma y, a function in two variable which is defined by x square plus y square. I'm talking about the function derivative of the function f at x at 0, 0. And then by definition, it will be f of 0, 0, f of 0, 0 plus h times 1, 0, because this is a vector in the direction of x minus f of 0, 0. But as I said, this part will simply turn out to be f of h, 0 minus f of 0, 0 divided by h. Substitute h, 0 here in the function. So f of h, 0 simply turns out to be h square plus 0 square, and f of 0, 0 by putting the value here, 0 is 0. Now, simplify this, and this turns out to be h. This is limit h going to 0, h, and hence the answer is 0. I hope you have understood how to execute the definition, right? Now, in case you have understood how to execute the definition, I hope you can take a minute. I'll give you a minute right now. Can you tell me what will be the value, what will be the formula for f of dou f by dou y at 0, 0? It is limit k approaching 0, f of. One of you have to unmute yourself and answer. The one who's willing to unmute and answer can do that. I will get an idea whether you have followed the definition.
F of 0, k.
It is f of 0, k minus f of 0, 0 divided by k. And you can simplify this. You will observe that on solving this, this will be simply k square minus 0 upon k, and hence it is limit k approaching 0, and hence 0. So this is how you can apply the definition of a directional derivative and get the you can apply the definition of directional derivative in the direction of a standard basis, that is 1, 0 and 0, 1, to obtain the partial derivative of f with respect to x and f with respect to y. So that is the concept of partial derivative, okay, theoretically. But when it comes to solving a problem, definitely I'm not going to do this way. There is a better way of handling the question. So suppose you have been given a function, let us say x square plus y square plus xy, and you are supposed to calculate the partial derivative of f at with respect to x and y, okay, at x and y, okay. So the simple rule goes this way. The simple rule says, if you have a function, let me take the same function here, f of x comma y, which is x square plus y square plus xy. Okay. Now, if I'm talking about dou f by dou x, so it is a partial derivative of a function with respect to x. Now, when I'm treating this, when I'm taking a partial derivative with respect to x, I'm going to treat y as constant. Okay. So the derivative of x square will be 2x. Derivative of y square, since y is constant with respect to x, it will be 0. And derivative of xy will be y times derivative of x. So the answer is 2x plus y. Now, if you have understood the concept, at your end, try applying the definition and get the answer for partial derivative with respect to y. Okay, you can just check the answer. I'm listing the answer on the board. You can see the answer. The answer is 2y plus x. Right? This is the answer, 2y plus x. Now, the interesting questions which come in the jam. This is one of the questions what I had seen in the jam. That's why I'm sharing this with you. So here the function f of x comma y given by x into sine 1 by x plus y into sine 1 by y, where x and y, x comma y is not equal to 0. Basically, it is x into y not equal to 0, and 0 if it is 0. I want to show that dou f by dou x at 0 comma t is 0, and dou f by dou y, that is partial derivative of f with respect to y at 0 comma 0 does not, they don't exist. So if I'm looking at dou f by dou x, now this function has to be defined in a different manner, but let it be for now. So I have function f of dou f by dou x at 0 comma 0 given by f of 0 plus h comma 0 minus f of 0 comma 0 divided by h, where h is going to 0. Okay, so it is only limit h approaching 0, f of h comma 0 minus f of 0 comma 0 divided by h. Okay, now the value of f of h comma 0, okay, will be h into sine 1 by h. Now, if you ask me why, if I put y equal to 0 here, this is a bounded function. Sine is bounded function. So when y equal to 0, whatever is the value of this will be between 1 and minus 1. So 0 times sine, whatever value is, this will become 0. So I can simply take this value as h into sine 1 by h minus 0 divided by h. And now on cancelling h, I come across a limit sine 1 by h when h equals to 0. And in the beginning of my session, I had mentioned that this limit does not exist. Okay, this limit does not exist. Now, on a similar way, you can argue for dou f by dou y. So if you take dou f by dou y at 0 comma 0, it will be 0 comma k, and you will be able to see dou f by dou y does not exist at 0 comma 0. Okay. As I had said, this is a question which is similar to one of the JAM questions that I had already checked somewhere. So this is a function for which the partial derivative don't exist, but it is continuous. The reason is, you can check the continuity of this function. So you consider mod of f of x comma y minus 0 comma 0. F of x comma y is x into sine 1 by x plus y into sine 1 by y. Observe that this value is greater than or equal to 0. I can say the function is continuous at 0, 0 if the limiting value of f of s comma y is equal to f of 0, 0. Other way I can say that the difference between these two values is 0. Okay. So I'm going to prove that modulus value is 0. So f of x comma y is x into sine 1 by x plus y into sine 1 by y. F of 0, 0, above you can see it is given to be 0. Apply triangle inequality. So you have this modulus less than or equal to mod x into sine 1 by x plus mod y into sine 1 by y. Since sine being a bounded function, this will be less than or equal to 1, and hence this expression is smaller than or equal to mod x plus mod y. You can put x equal to 0, y equal to 0 safely here, and you get the value 0. So what I can see is this particular limit xy going to 0, 0, mod of f of x comma y minus 0, 0 is sandwiched between zeros, and hence the limiting value of f of x comma y, limiting value of xy approaching 0, 0, f of x comma y is f of 0, 0, leading to the conclusion that the above function is continuous but the partial derivatives don't exist. That is what I have mentioned over here. Now, similarly, you can try the other example. Okay, no, sorry, this is the conclusion about the above example. Okay, now moving on to the differentiability of a scalar valued function. A function is a scalar valued function f from S to R. I have f a function from S to R where S is a subset of Rn. Particularly, it's an open set, non-empty open set, and A is a point. Now, if S is open, A becomes the interior point. Then f is said to be differentiable at x equal to a if I'm able to find a linear transformation T from Rn to R such that the limit h going to 0, f of a plus h minus f of a minus th upon norm h is equal to 0. The linear transform T is called the total derivative of the function, and it is denoted by notation. We all know that every linear transform Tx is of the form Ax, where A is a matrix. So if I'm able to find out this particular matrix, I know who is the total derivative. Okay. Now, how to calculate this total derivative or DFA? So here, let us visit a concept called gradient of a scalar value function. Okay. So if I have f a scalar value function and a is an element of S, then gradient of f at x equal to a is given by it is nothing but a vector where first component is do f by do x1 at a, second component is do f by do x2 at a, and the last component is do f by do xn at a. Okay. Let us see, we have an example over here. So I have f of x comma y given by 6x square y plus 7xy. I want to calculate the gradient of this at any point x comma y. Okay, so as there are two coordinates, this is a function of two variable here. So I will have gradient of vector which will have two coordinates. The first coordinate will be the partial derivative of f with respect to x. The second coordinate will be partial derivative of f with respect to y. So if I look at this function and if I have to calculate the partial derivative of 6x square plus 6x square y plus 7xy, take a derivative of this with respect to x by treating y constant. So the derivative of the first term with respect to x will be 12xy. The derivative of the second term with respect to x will be 7y. Okay. Apply the same logic to calculate the derivative of f with respect to y. The derivative of the first term with respect to y by treating x constant will be 6x squared. The derivative of the second term with respect to y by treating x constant is 7. So the gradient of the function f at a point x comma y is 12xy plus 7y comma 6x squared plus 7x. Now, if you want it at a particular point, put the value of x. Suppose, for example, I want it at 0, 0. I'll put x equal to 0, y equal to 0. So my answer of the gradient value is a vector 0, 0. And you can work it out for the remaining part. Okay. Now, we have to understand what is the relation between a gradient and the total derivative of a scalar value function. So, I have a function f from Rn to R. A is an element of S, which is the domain of f. then gradient, if the gradient of f exists and if the function is differentiable, then their total derivative of f, that is the matrix what I said, no? The total derivative of f at a, which is nothing but t, the linear transformation, is the vector grad f at a. There is a vector grad f at a. Okay, so let us try this through an example. So the question is, find the total derivative of the function 3x cubed y plus 7y sin x plus e raised to xy at 1, 1. Okay, so as I said, the total derivative is at the point 1, 1. So the total derivative will be grad f of a. Now the grad f of a, this is a function of two variables. So I need to calculate derivative of f with respect to x at 1, 1, derivative of x, f of x comma y at 1 with respect to y at 1, 1. Okay, now first let us, okay, so let us calculate derivative of f with respect to x, okay, for this function. So again, by treating y constant, the derivative is 9x square y plus 7y, derivative of sin x is cos x, plus derivative of e raised to xy with respect to x is e raised to xy into y. Now I want derivative of f at 1, 1. So put x equal to 1, y equal to 1. So it is 9 plus 7 into y is equal to 1 cos of 1 plus e. Okay. Now derivative of f with respect to y, that is dou f by dou y. Treat x constant and differentiate with respect to y. So the first term derivative with respect to y is 3x cubed. The second term's derivative with respect to y is 7 sin x. And the third term derivative with respect to y is x e raised to xy. Evaluating that at 1, 1, I get the answer 3 plus sin 1 plus e. So the total derivative at 1, 1 is grad f at 1, 1. So this is the value of dou f by dou x at 1, 1. This is the value of dou f by dou y at 1, 1. As you can see over here, that is the total derivative. Okay. So that is how we calculate the total derivative of the function of a scalar valued function. Now let's observe some of the properties of a scalar valued function and let us see how they are useful in solving the problems. Okay. So if I have a scalar valued function which is differentiable, then it is continuous. Okay. So this is a very popular result. You are able to find the total derivative of a function, or if you are able to check the definition of a differentiability of a scalar valued function, and if it turns out to be differentiable, it is continuous. It can be used other way around. Okay. If my function is not continuous at a, certainly it is not differentiable at a. So let us have the look at this function. I have a function f of x comma y given by xy upon x square plus y square if x comma y is not equal to 0, 0, and 0 if x comma y is equal to 0, 0. I want to show that it is not differentiable. Okay. So observe the function here for xy not equal to 0, 0. What you will observe that the numerator and denominator both are the homogeneous polynomial of degree 2. On top of that, the power of x and y are equal in the numerator and denominator. In such case, I will go for evaluating a limit along a path. Okay. So consider limit. I can prove it is not continuous by showing the limiting value of f of x comma y at 0, 0 does not exist. So consider L as the limiting value of xy approaching 0, 0 f of x comma y, and here the value of f of x is xy upon x square plus y square. So now, as I said, since the power of x and y are equal and the total degree of the numerator is same as total degree of the denominator, the path which I will choose is y equal to mx. Okay. So when I put y equal to mx, I can see that entire x gets cancelled. And my answer turns out to be, the limiting value turns out to be m upon 1 plus m square. Again, the selection of m is arbitrary. So the limit depends on m. Hence, the limit is not unique and hence it does not exist. Therefore, the function is not continuous at 0, 0. And by using the above result, a function which is not continuous Need not be different. It is not differentiable. So I'm able to do the differentiability of this function. Okay, I'm able to check the whether I'm able to prove the function is not differentiable with the help of proving it is not continuous. Now going down, there is a beautiful relation what the total derivative or the gradient share with the directional derivative. Okay, so here is an interesting result which says fx is a differentiable function at x equal to a, and u is a unit vector. Then if the function is differentiable, the first thing is directional derivative exists in all the directions. Okay, now this result can be used other way around. The first thing is, if the function is differentiable, you are able to find duf for all u's. But suppose there exists a u such that duf doesn't exist at a, then the function is not differentiable at a. Okay, so the contrapositive statement is equally strong if you have to prove the function is not differentiable. But right now, my aim is something different. My aim is to see how to calculate the directional derivative with the help of gradient. Okay, so if the function is differentiable at x equal to a, and then the directional derivative exists in all the directions. And secondly, duf at a, okay, it is simply a dot product of gradient of f at a and u. Now, since this dot will not be visible, I have used the symbol of inner product. But when I'm referring to an inner product, here I'm referring to a dot. So it is a dot product of gradient of f at a and u. Okay. Now let us see how to implement this. So here is a very nice question. I have f of x comma y given by x cube plus y cube divided by x square minus y square if x square is not equal to y square, and it is 0 if x square is equal to y square. My question is to find the directional derivative of f at 0, 0 in the direction of u, where u is a vector 4 by 5, 3 by 5. This is one of the JAM paper questions, but I have not mentioned the year over here. Towards the end, I will share the question bank from JAM exam what I have taken. Okay, first I need to confirm whether this u is a unit vector. So the best thing is find out the norm. You can check the norm of u. Norm of u is under root the first coordinate 4 by pi square plus 3 by pi square. It will turn out to be 4 square plus 3 square divided by pi square, and then that turns out to be 1. You can verify that, check. Okay. Now, if I'm using this formula, as I said, I have a formula here. We have a highlighter here. Okay, so I have a formula here. Okay, that the directional derivative is given by the dot product of gradient of a and the unit vector. So I already have proved u is a unit vector. So my unit vector is ready. I just need to calculate the gradient at the point A. So I have to calculate directional derivative at 0, 0. So we'll evaluate the gradient at 0, 0. To calculate gradient at 0, 0, we need to evaluate the partial derivatives at 0, 0. So let us go for dou f by dou x at 0, 0. By definition, it is limit h going to 0, f of h comma 0 minus f of 0, 0 divided by h. In the function, you substitute the value. Okay, make a substitution here. So this is h cube plus 0 cube divided by h square minus 0 square. That will give me h cube upon h square term minus f of 0, 0 is 0 divided by h. Okay, simplify this, you will get dou f by dou x at 0, 0 equal to 1. Okay, similarly, dou f by dou y, it is limit k approaching 0, f of 0, k minus f of 0, 0 divided by k. Substitute the value. This is my function.
Ma'am,
Yeah, am I audible?
yes, ma'am.
Yeah, what was the question? I can't see your chat, so I really don't know what is the question.
Okay, Dipali, for
Uh,
few moments your voice was not there, that's why.
Okay. Yeah, that is because I'm using the mobile data.
Okay.
If I can do that. Okay. So now you take a dot product of these. I hope my screen is visible.
Yes.
Yeah. So you take a dot product of these two and you will see the directional derivative of f at 0, 0 turns out to be 1/5. Okay.
ma'am,
Now as yeah.
ma'am, in this question, but we have to clarify the function is differentiable. Then only we can apply this one. No?
Sorry.
Example, in this example one, now in this
Yeah.
we have to check the function is differentiable. No, first.
Yeah. In this case, I'm assuming it is differentiable. I avoided doing that part. Okay.
Okay.
Yeah, I'm assuming that I thought I'll just cover up the example. I was in a hurry to demonstrate the formula. Okay, but one can check. You have to verify that condition f of a plus ch minus f of a minus your t times h. Now t times h will be grad of. I will come to that point. Just give me a moment. I will come to that point. How to calculate t of h. It is coming ahead. Towards the end, I have taken
Okay,
one
ma'am.
example. Just give me a minute. Okay. So here is another example which you can try on your own. So my f of xyz is given to be x square plus y square plus z square, and a is a vector 1, 1, 0. And let us say u is a unit vector in the direction of I minus j plus 2k. You have to calculate u f at k. So observe that this is not a unit vector. Okay, u is a unit vector in the direction of this. So first you have to calculate u, and then you can use the above formula to get the directional derivative. Okay. Now, before I go ahead with this example, this is something which I had seen in the JAM question paper. A similar kind of example I have ahead, wherein I use the parameterization of the curve. So first, let us discuss that example, and then I'll come back to this one. Okay. This is one very nice example to see how the parameterization is used to find the directional derivative. So the question goes this way: find the directional derivative of f of x comma y, which is x square minus 3xy at 1, 2 along a parabola y equal to x square minus xy plus 2 at 1, 2. Okay, my function is here, my point is here. I can calculate the gradient. Okay, so gradient calculation is not a problem, right? So I have a function f. The first partial derivative of f with respect to x is, you can calculate now, this is 2x minus 3y, and at the point 1, 2, dou f by dou x at 1, 2 is minus 4. You can substitute the value and verify. Similarly, derivative of x with respect to y is minus 3x, and dou f by dou y at 1, 2 is minus 3. So my gradient is ready. The challenge, the second part what I need over here is the unit vector in the direction of parabola. So the unit vector in the direction of parabola is basically a tangent vector. Wait a minute. So a vector in the direction of parabola at 1, 2 for the curve y equal to x square minus x plus 2 is a tangent vector at 1, 2. Now how do I get a tangent vector? So here is the process. What you have to do is you have to represent the parabola in a parametric form. So if I take x equal to t, I have y is equal to t square minus t plus 2. Okay. So the tangent vector at 1, 2 is a vector dx by dt, dy by dt. So when x, y is equal to 1, 2, you can put x equal to 1 here and y equal to 2 here. You will observe that the value of t turned out to be 1. Okay, so this is my x, the derivative of x with respect to t is 1. So dx by dt at 1, 2 is 1. This is my y, differentiate y with respect to t. You will have dy by dt is equal to 2t minus 1. So put t equal to 1 here, the derivative of y with respect to t at this point will be 1. So your tangent vector turns out to be 1, 1. So unit tangent vector will be v upon norm v. That is 1, 1 divided by norm of 1, 1, which is under root 2. So u is 1 by root 2, 1 by root 2. So now, since my unit vector is ready, my gradient is ready, I can calculate the directional derivative, which turns out to be minus 7 by root 2. Okay. So if a curve is given and you're supposed to find the directional derivative of the curve, what you need to calculate is a unit vector along the tangent vector of the curve. Okay. Now I'll go back to my example, which I had said I'll do it after 2 minutes. Now instead of any random curve, let me take a line. Okay. So this is the question, as I said, from one of the JAM paper. So I have phi of x, y, z given by dy square plus dy z for x, y, z belonging to R3. The question is find the absolute value of the directional derivative of phi in the direction of the line x minus 1 upon 2, y minus 2 upon minus 1, sorry, y minus 2 upon minus 1 plus z equal to z upon minus 2 at the point 1, minus 2, 1. The function is given, the point is given, I can calculate my gradient. Okay, so let us see the calculation of the gradient first. Okay, the function, maybe I should have written the function over here. No, I have not written the function here. Okay, so 3y square plus 3yz. So this is the function what I have. Now as you can see here, the function is a function of y and z only. So the derivative of it with respect to x is 0 for every value of x, y, z. Particularly at the point 1, minus 2, 1, it will be 0. To differentiate this with respect to y, the derivative is 6y plus 3z. And now at the point 1, minus 2, 1, the value turns out to be minus 3. Differentiate this with respect to z, the answer is 3y. At the point, it is 3. So my gradient is 0, minus 9. So gradient is ready. Now coming to the unit vector in the direction of the line. Now when it is a line, okay, you can have the parametric equation of this line. You can take this entire value. So maybe you can take this entire value as t, okay, and you can simplify as I had done in the earlier case. Okay, so I have x minus 1 upon 2 equal to t. So this gives me x is equal to 2t minus 1. So now if I'm talking about dx by dt, that will turn out to be 2. Similarly, y minus 2 upon minus 1, which is equal to t, you can have y is equal to minus t plus 2, which means dy by dt is equal to minus 1. Similarly, you can check dz by dt turns out to be 1. Dz by dt turns out to be minus 2. Not 1, sorry, minus 2. Okay, and you can observe that these values are basically the direction cosines here. Okay, so my vector v along the line is 2, minus 1, minus 2. Okay, so let v be the vector in the direction of the above line, then v is equal to 2, minus 1, 2. Those are precisely the directional cosines of a line. And then you can find a unit vector in the direction of v. Okay, that is v upon ln v. That turns out to be 2 by 3 minus 1 by 3 minus 2 by 3. Substitute them and simplify in the formula. So gradient of f into the unit vector u, the dot product, and the answer turns out to be 1. Okay, that's how you can find the directional derivative of a function along a particular curve. Okay, now here are some results which will be useful. So the question is the directional derivative, at which direction the rate of change of function is maximum. So here is the result which says that the directional derivative du f is maximum if u is a unit vector in the direction of grad f, and it is minimum if I take a vector which is orthogonal to grad f at A. Okay, and how will you find the vector which is orthogonal to grad f at A? The dot product of that vector with grad f at A should be 0. Now, why it is so? Okay, so let us understand this. This may be useful ahead. So suppose switching the page. Okay, so the maximum rate of change of f of x at x equal to A. Maybe I'll explain it over here. I'm not able to scroll down. So du f at A is basically given by the dot product of grad f of A times u. Okay, so by formula of a dot product, this is equal to norm of grad f of A into norm of u into cos theta, right? Norm u is 1, so this will simply turn out to be norm of f of A into cos theta. Now this will be maximum if cos theta takes its maximum value, and the maximum value of cos theta is 1. Okay, so this is maximum if and only if cos theta is 1. Now cos theta will be 1 if and only if theta is 0. Okay, this is possible if and only if u is along grad f of. Okay, that is what I had mentioned some time back. So the directional derivative is maximum if u is a vector along grad f of. Fine. Now, suppose I'm talking about the minimum value. If I'm talking about the minimum value of grad f of A, once again, that will be possible if I'm talking about the minimum value in terms of magnitude. Let me be precise. So I'm talking about the maximum absolute value and the minimum absolute value. Okay. Knowing that these values have a sign, I will discuss that in the next example. Let us talk about the absolute value. So minimum absolute value, the minimum absolute value will be 0. Okay, so this should be 0. This will be 0 if and only if norm of grad f of A. Okay, so this is possible if and only if cos theta is 0. Cos theta will be 0 if and only if theta is equal to pi by 2. Okay, so the highest absolute value of directional derivative is obtained when u is a vector along gradient of A, and the minimum value or the directional derivative will be 0 only when I'm taking a vector u which is perpendicular or orthogonal to grad f of A. Okay, so here I'm talking about maximum rate of change. Once again, I'm talking about the absolute value, maximum rate of change or the maximum absolute value of a unit, directional derivative is obtained when I'm taking u is equal to a vector along the direction of grad of f, and the minimum value or the rate of change, the directional derivative will be 0 if I'm choosing a vector which is orthogonal to grad f of A. Okay, so here we have calculated a maximum rate of change of the function f of x comma y, where which is nothing but log of x plus y plus z at 1 comma 2 comma 3. So once again, when I'm saying maximum here, I am dealing with the absolute value. So we already have a result. The maximum rate of change of f of x comma y comma z is nothing but directional derivative of du f at a, where my u is along grad f of a. And now if you simplify this, and I forgot to do that over here, and I'm not able to scroll properly here. So if my u is equal to grad f of a upon norm of grad f of a, okay, when I substitute this in the formula of duf, okay, so the maximum value of duf at a, this is nothing but inner product of f of a along with the unit vector u, which is grad f of a divided by norm of grad f of a, which will simply turn out to be norm of grad f of a square divided by norm of grad f of a, which is norm of grad f of a. This is the highest value of the directional derivative. Highest directional derivative. So the maximum rate of change of f of x comma y comma z at the point 1 comma 2 comma 3 is the norm of gradient of f at 1 comma 2 comma 3. Okay, so my function f of x comma y comma z is given to be log of x plus y plus z. So if you take a derivative of f with respect to x, so it will be 1 upon x plus y plus z into derivative of x plus y plus z with respect to x, which will turn out to be 1. Okay, we can check that over here. 2f by 2x. It is 2 by 2x of log of x plus y plus z, which will be 1 upon x plus y plus z into derivative with respect to x of x plus y plus z, and observe that y and z are constant when I'm differentiating with respect to x. So this will simply turn out to be 1 upon x plus y plus z. Okay. Similarly, you can try dou f by dou y and dou f by dou z. You will get the same answer. At the point 1, 2, 3, it is the value is 1 by 6, comma 1 by 6, comma 1 by 6. That's the value of the gradient. Okay. The maximum rate of change at 1, 2, 3 is modulus norm of gradient of f at 1, 2, 3. So that is under root of 1 by 6 square plus 1 by 6 square plus 1 by 6 square. On solving, you get the value 1 upon 2 root 3. Okay. Now here is a note. You can actually prove this note. I have given a proof down. Okay. So f of x increases rapidly when the dynamics of gradient of f of x y z. Okay. So why it happens so? So du f of L will increase rapidly if grad of f of a into a. This is maximum value. And this is not a, actually this is u. Okay, if the dot product is maximum. The dot product will be maximum if the cos theta is 1. The cos theta will be 1 if theta is 0. So u has to be along the direction of f of it. Whereas the rate of change of this will be minimum, okay, if this inner product value is minimum. The inner product is given by norm of gradient of f, norm of u into cos theta. So this will be minimum if theta is minimum. Cos theta is minimum. Cos theta minimum value is -1, which is obtained at 5. And hence the result. So u has to be in the direction of minus of gradient of f of a. So I have a function f given by 9x cube plus 5y square. You can calculate the gradient. The first term is derivative of f with respect to x. So derivative of 9x cube with respect to x is 27x squared. Okay, and derivative of f with respect to y, that will be simply a derivative of 5y squared with respect to y, that is 10y. Okay, so the function increases rapidly at 2, 1 in the direction of gradient of f at 2, 1. So this is my gradient, put x equal to 2, y equal to 1. So this is the direction 108, 10. In this direction, my directional derivative will be maximum, and it decreases rapidly. The rate of change of function will be, the function will decrease rapidly in the direction of negative of the gradient. And that's why this is the answer. Here is a result, which is a very popular result, which says that if I have a function f from Rn to R, and A is an interior point, so if I have a function, if all the derivatives exist, if all the partial derivatives exist and continuous, I can say that the function is differentiable. However, the converse is not true. If I have a function is differentiable, okay, the partial derivative may not exist, or if they exist, may not be continuous. Towards the end, we have an example here. So here is one example. I have a function f of x. Okay, so I have a partial derivative. Look at this function. As I said, so existence of partial derivative is not sufficient to guarantee the differentiability of the function. Okay, so I have a function f given by 2xy upon x square plus y square when xy is not 0, 0, and 0 when xy is 0, 0. Now you can observe that this function is not continuous. The logic remains same. You can see that numerator denominator both are the polynomial of degree 2, and the power of xy is equal, x and y are equal in numerator as well as denominator. So I can evaluate the limit xy going to 0, 0, f of x, y along y equal to mx, and we'll see that the answer depends on m. I have done the calculation ahead, but just to give you a hint here, the limit doesn't exist, so it is not continuous, hence it is not differentiable. Anyway, the detailed calculation will approach ahead. Okay, first let us confirm whether the derivative exists, partial derivative exists at 0, 0. So here I have dou f by dou x. Okay, dou f by dou x at 0, 0, it is limit h going to 0, f of h, 0 minus f of 0, 0 divided by h. Put the values over here. F of h, 0 from here is 0, it is 0. Okay, f of 0, 0 is 0. I can see that the derivative of f with respect to x and 0, 0 is 0. Similarly, you can calculate dou f by dou y by using a definition, and that turns out to be 0. Now coming to a differentiability part. As I have said, the function, if I'm evaluating the limiting value of the function at 0, 0, it will be limit xy going to 0, 0 to xy upon x square plus y square. So along the path y equal to mx, the limiting value turns out to be 2m upon 1 plus m square. And it depends on m, which is an arbitrary constant. So the limit is not unique, hence it doesn't exist. Since this limit doesn't exist, the function is not continuous, and hence it is not differentiable. So existence of partial derivative is not sufficient to guarantee the differentiability of the function at a point. Okay, from here onwards. Okay, so when it comes to a partial derivatives, we also have an interesting theorem which is called an Euler's theorem. So let's see the definition of the statement of an Euler's theorem. Many a time this is very useful. I have just kept a simple demonstration how the Euler's theorem is applied. So Euler's theorem for the homogeneous scalar valued function. Most of the questions which we see in the exams have maximum 3 variables. So I'm restricting myself to 3 variables. So I have a function f of x, y, z, which is homogeneous function of degree n. Now what is homogeneous function? So f of tx, ty, tz will turn out to be t raised to n times f of x, y, z. example, I have kept it down. We'll see after 2 minutes. So if the function is homogeneous function of degree n, then it sees x into dou f by dou x plus y into dou f by dou y plus z into dou f by dou z at any point x, y, z is n times f of x, y, z. Okay, so as an example, look at my function f of x, y, z, which is given by x cube plus y cube plus z cube. You can see it's a homogeneous function of degree 3. How? You replace x by tx, y by ty, z by tz. So this will be tx cube plus ty cube plus tz cube. This is t cube times x cube plus y cube plus z cube. And this is precisely my f of x, y, z. So from this power of t, I can say that it's a function, homogeneous function of degree 3. Then by Euler's theorem, x into dou f by dou x plus y into dou f by dou y plus z into dou f by dou z is 3 times f of x, y, z. Okay, I'm not doing any question of verifying an Euler's theorem over here, as we normally do not have verification kind of questions in the competitive examination. But if you come across any such left-hand side, okay, wherein your function is homogeneous, you can directly apply Euler's theorem and conclude that the result is 3f of x, y, z. These questions are very popular in the objective part. Okay, there's something called a chain rule, which we have already seen for the composite functions in a real valued functions of real variable, but it is also applicable for the scalar value function. I have a function f, which is a function of x and y. X and y are independent variable, and x is a function of t, y is also a function of t, making f as a function of t. So I can calculate the total derivative of f with respect to x as dou f by dou x into dx by dt plus dou f by dou y into dy by dt. Okay, this is a particular chain rule I'm taking here because I can use it for the questions where the parameterization is due. Okay, the chain rule is much more wider than this. Okay, I'm just touching a chain rule and going from here. I'm not saying this is the only statement of chain rule. You have a more advanced or general statement of chain rule, which you will find in any book of calculus. Okay, so here is one example. I wanted to attempt this question, and that's the reason why I stated the chain rule in that particular format. So I have a function f of x comma y given by 3x cubed y plus 4y cubed. And my x is equal to sine phi t, y is equal to cos phi t. My z is nothing but my f of x comma y. I'm sorry, I should mention that. So let z is equal to this. Okay, so my question is find dz by dt at t equal to pi by 2. The job is simple. dz by dt is equal to dou z by dou x into dx by dt plus dou z by dou y into dy by dt. Okay, now if t is equal to pi by 2, okay, t is given to be pi by 2. The value of x is sine phi t. So value of x at t equal to pi by 2 turns out to be 1. Y is given to be cos phi t. So the value of y at t equal to pi by 2 turns out to be 0. Okay. Now applying the chain rule, my function again. I can see my function now. Okay, so here is my function. The first term is dou z by dou x. Dou z by dou x is the derivative of this function with respect to x. So the derivative of this function with respect to x, second term is y, derivative is 0 with respect to x. For the first term, the derivative is 9x squared y. Okay, into dx by dt. My x is sine phi t, the derivative of sine phi t is pi cos phi t, plus dou z by dou y. So derivative of this with respect to y is 3x squared plus 12y squared, and derivative of yt, y is cos phi t, so it is minus pi sine phi t. Okay, substitute the value of substitute the value of x and y in these expressions, and you will see that the answer turns out to be minus 15. So this is a simple question which can be done by using chain rule. But as I said, I have done that specific chain rule because I wanted to attempt this question. Okay, moving on to the last segment of my session, that is the label curve, normal vector, and the tangent plane. Okay, so what is a level curve? You take a scalar valued function and equate it to a constant. So the set of all S, the set S of all the vectors x1, x2, xn belonging to Rn, which will satisfy the condition f of x1, x2, xn equal to C. Okay, that is called a level curve. There are conditions on f, that f has to be a differentiable function. So let me just give you an example of a level curve. So if I take f of x comma y is equal to x square plus y square, and if I take f of x comma y equal to 1, so it is an equation x square plus y square equal to 1. So the level curve in this case is a standard unit circle. Okay, moving on to the normal vector and the tangent plane. Okay. So if S is equal to, again I'm restricting myself to R3 now. I'm not getting into general Rn. Let's take ourselves to R3. I have S is equal to a set of xyz, which will satisfy the condition f of xyz is equal to k. It's a level curve. And A is a point in S. So A equal to A1, A2, A3 belongs to S. That means A is a point on this curve. Okay, on the surface. Now, not the curve, I'm in 3 dimensions, so it's a point on a surface. Right? Then the vector, which is gradient of F at A, this is called normal to the surface. Okay, and the plane containing all the tangent lines of the surface at x equal to A forms a plane which is called the tangent plane. Right? So that is a concept of maybe I don't know whether I'll be able to draw over here. I'm not sure whether I'm good at drawing this. Let me just give it a try. So imagine this is a sphere, okay? Then maybe sorry. If this is a sphere, now this is, it is difficult to draw a tangent plane, but now imagine a plane in the direction. Assume that the z-axis is coming towards, the z-axis is coming towards you, so you can imagine a plane here. So this plane contains all the tangent to the curve, to the sphere. Then the normal vector is the one which is perpendicular to this. Okay, so this vector is nothing but, suppose if this point is A, then this vector, the vector along this line is grad f of A. This is grad f of A. Okay, and this is your tangent plane. Now the equation of a plane is always given by 2 things. To write an equation of a plane, you need at least one point on the plane, and what you need is a normal vector. So this is your normal vector. This is your normal vector, right? So you have a normal vector and you want to find equation of a tangent plane. So I have a point A. Let us say the point A is given by A1, A2, A3. Okay, and my normal vector grad of f is dou f by dou x at A, dou f by dou y at A, and dou f by dou z at A. Okay, then the equation of a tangent plane is basically a dot product of grad f at A with a vector x minus a1, comma, y minus a2, comma, z minus a3. Okay, so equal to 0. So my equation of a tangent plane, I have done that over here. So I'll switch back to my notes. Okay, so the equation of a tangent plane, if I'm taking a dot product, which I was explaining over here. So the dot product will be x minus a1 times dou f by dou x at A plus y minus a2 times dou f by dou y at a equal to 0. Okay, that is precisely I have mentioned over here. Okay, now you have a questions in the JAM examination of finding the equation of a normal line. Now I have just given you what is called a normal vector. How to find the equation of a normal line, we'll do it in a minute. But you have a question of either finding a normal line or finding the equation of a tangent. So now to find the equation of a tangent plane, I need two things over here. So I need a normal vector and I need a point. Okay. So if I have the point and a normal vector, I can find the equation of a tangent plane. So going back to my expression here. So my curve is given. Okay. This is a curve in 2 dimensions. So this is a surface in 3 dimensions. So my level surface is z is equal to 9x square plus y square plus 6x minus 3y plus 5. So let me write it in the form of f of x, y, z equal to 0. So my f of x, y, z is z minus 9x square minus y square minus 6x plus 3y minus 5 equal to 0. To find the gradient, I need the partial derivative. So calculate dou f by dou x. Okay, which is from here, if you differentiate, it is minus 18 minus 6. Dou f by dou y, so it is minus 2y plus 3. And dou f by dou z, it is 1. Okay, I need to find the tangent plane at the point 1, 2, 3. So evaluate these partial derivatives at 1, 2, 3. So dou f by dou x at 1, 2, 3 is minus 24. Put x equal to 1 here and you will get the answer. Dou f by dou y at 1, 2, 3 is minus, this is minus 24, dou f by dou y is minus 1 and dou f by dou z is 1. So your normal vector is minus 24, minus 1 and 1 at the point 1, 2, 3. Okay. Now I will come to normal line after 2 minutes. Let me finish the calculation for a tangent plane. Okay. So equation of a tangent plane. As I had mentioned 2 minutes back, it's a dot product of gradient at a into x minus a1, comma x minus a2, comma y minus a2, comma z minus a3. So it is 3 into y minus a. Dou f by dou z at 1 to 3 into z minus 3. Putting this over here and simplifying, your z minus 24x minus y plus 23 is a tangent. Okay. Now going to a normal line. I know a normal vector, right? So equation of a line passing through, okay, ABC in direction of L I bar plus N G bar plus N K bar is given by x minus a upon L equal to y minus b upon m equal to z minus c upon n. That's an equation of a line in 3 dimensions. Okay. So now I know my normal vector. My normal vector is minus 24, minus 1, 1. So I want my line in this direction and my normal line has to pass through. So here, so my normal line passes through the point 1, 2, 3 and it is in direction of the vector minus 24, minus 1 and 1. So I think that justifies the equation of a normal. Okay. Now we'll see the concept of higher derivatives, that is the second order derivatives, and these are something which are important to discuss the question of local maxima, local minima, saddle point, and so on. So first of all, the second order derivatives. I'm just restricting myself to second order derivative and I'm going to discuss only the question of maxima and minima. Okay, so I have f of x comma y. The second order derivative dou square f by dou x square, dou square. There are 3 types of second order derivative possible. If I take a function in 2 variables, I have the second order derivative with respect to x, second order derivative with respect to y, and the second order derivative with respect to x and y. But the catch over here is as I have dou square f dou x dou y, I also have dou square f dou y dou x. Now the question is, how do I define them? Dou square f dou x dou y is nothing but dou by dou x acting on dou f by dou y. Okay, and dou square f dou y dou x is dou by dou x, sorry, dou by dou y acting on dou f by dou x. Now the question is, are they equal? Let us answer that question after a minute. Let us understand how to calculate them. Now the example what I have taken here, these are called the mixed derivatives. They are called the mixed derivatives. Okay. Now equality of the mixed derivatives requires some assumption, and I will discuss it only after I finish this example. So I have f of x comma y given by 3 sin x plus y cos x. So first order derivative dou f by dou x is 3 into derivative of sin x, which is cos x, plus y into derivative of cos x, which is minus sin x. And dou f by dou y is cos x. You can check it on your own. Take the first dou square f by dou x square, which stands for 2 by dou x of dou f by dou x. So it's a derivative of 3 sin x minus y sin x. If you differentiate this with respect to x, the answer is derivative of cos x is minus sin, so minus 3 sin x, minus y into derivative of sin x, that is cos x. Okay. I should have discussed dou square f by dou y square. I have done that over here. Dou square f by dou y square is dou by dou y of dou f by dou y. And dou f by dou y is a function of x alone. So dou f by dou y is 0. So dou square f by dou y square is 0. Now coming to the mixed derivative, I already know for this example, the mixed derivatives are equal. So here I have taken dou square f by dou x dou y is same as dou square f by dou y dou x. And this is basically, I have explained here how to calculate. Okay. So if I use this formula and calculate, the answer turns out to be minus sin x in both the cases. Okay. Now the question arises, what is the condition for the equality of mixed partial derivatives? So the mixed partial derivatives are equal if they are continuous function, otherwise no. Okay, if they are continuous at a point a comma b. Okay. Now moving to the last segment of my session, local maxima, local minima, and saddle point. Okay. Now finding the maxima minima is always the important part of important study of calculus. So first of all, understand the definition of a stationary point. So I have a function f from S to R such that f is differentiable at x equal to a. Many of our functions, which are basically the combinations of, now I will not dig into the details of the split functions, which are defined differently at the point where we are taking a derivative and all. Okay, our life is normally simple for 90% of the problems what we attempt in the JAM examination. Your function normally is a function which is a combination of sin x, cos y, e raised to xy. Okay, these are all the nice functions what I put, or the polynomials in x and y. So I don't have to struggle checking the differentiability of this function. There are very rare functions, like I will show you towards the end, wherein the differentiability is challenged at the point x equal to a. But those functions are very rare, and you can handle them separately. But most of the time, checking the differentiability is not a big task. If your function is a combination, and when I say a combination, I'm talking about a function which is formed by using the algebraic operations like addition, multiplication, subtraction. Okay, again, division, you have to check whether the function is non-zero by which you are dividing. But most of the time, simple functions will be differentiable. So let us not worry about this. Okay. So if f is differentiable at x equal to e, then a is said to be a stationary point at f of x if gradient of f of a is 0. Okay, gradient of f of a is 0. Now there are three kinds of point in your domain which will exhibit this phenomenon. Okay. Now what are those three types of point which will exhibit this phenomena? So suppose I have a point A such that gradient of f of a is 0, and in a neighborhood of a, f of a is the biggest value. F of a is bigger than f of x. Then then a becomes a point of local maxima. Okay. Fine. Similarly, if gradient of f of a is 0 and You have a neighborhood of x where f of x is bigger than or equal to f of a. Then a becomes a point of local minima. But there is a third possibility that the gradient is 0 and I have a point gradient of f of a is 0, but in a neighborhood of a. I can always find f of x which is bigger than f of a, and I can always find another y such that f of y is smaller than a. So this situation says a is a point of minima, and this condition says a is a point of maxima. So such point is also called a minimax point, or we also call it as a saddle point. We have something called a second derivative test, which will help me to identify the local maxima, local minima, or a saddle point. Okay, if you are not able to draw the graph of the function, if you are not able to draw the curve, okay, then without drawing the curve or without drawing a surface, how to identify the stationary point is a point of local maxima, local minima, or saddle point. So here I need to take help of my second order derivative. So I have a function f, and a comma b is a point such that the gradient of f at a comma b is 0, leading to the conclusion that a comma b is a stationary point. It's a stationary point, right? Now let us calculate the second order derivative. So let capital A be equal to, this is capital A. Capital A is equal to dou square f by dou x square at a comma b. Capital B is equal to dou square f upon dou x dou y at a comma b. Capital C is equal to dou square f upon dou y square at a comma b. Now I'm taking capital delta is equal to AC minus B square. Okay. Now if delta is positive, I should have written this way. Okay. If delta is positive and A is positive, that is dou square f by dou x square. If this is positive, then a comma b is a point of local minima. Okay. If delta is positive and a is negative, then a is a point of local maxima. Okay. If delta is negative, then a comma b is a saddle point. And finally, if delta is 0, my test will be inconclusive. Okay, or I can say my test fails. So this is the second derivative test to identify the local maxima, local minima, and the saddle point. Now, I have just taken one example to demonstrate one of the question, but I have found a very good example in one of the JAM paper, which you should try. I think I have listed that example after this example. So I have f of x comma y given by x square plus xy plus y square plus 3x minus 3y plus 4. I have to find if there is a local maxima, local minima, and saddle point. Now, given a function may not have all types of stationary points. So you can have some, you can have a stationary point which could be a point of local maxima or local minima or a saddle point. So the behavior of the point will be decided only after you apply the second derivative test, right? So I have f of x comma y given by x square plus xy plus y square plus 3x minus 3y plus 4. Calculate the first order derivative. 2x df dou f by dou x is 2x plus y plus 3. Dou f by dou y is 2x, sorry, x plus 2y minus 3. Okay. So if I take a gradient is equal to 0. Now gradient stands for dou f by dou x at 0, 0 and dou f by dou y. Sorry. I'm not talking about a gradient at a point. I'm talking about a gradient at the point x comma y. So it is dou f by dou x and dou f by dou y. So if I solve the equation gradient equal to 0, basically I'm solving dou f by dou x equal to 0 and dou f by dou y equal to 0. Now dou f by dou x equal to 0 gives me my first linear equation, 2x plus y plus 3 equal to 0. My equation turns out to be 2x plus y equal to minus 3. Dou f by dou y is x plus 2y minus 3. That equal to 0 gives me my second linear equation, x plus 2y equal to 3. Now you can solve this by using the Cramer's rule. You can solve this by using the simultaneous equation. You can solve this by using your row echelon form. Whichever method you are comfortable with, you can use that, and you can check that on solving this, you will get a unique solution. Okay, you can check the determinant of the coefficient matrix is non-zero. So the system has a unique solution. So I will have x equal to -3 and y equal to 3. Solve this by whichever method you are comfortable. So I can see here there's only one stationary point, that is -3, 3. So there's a possibility that it could be a local maxima point, local minima point, or a saddle point. For that, I have to run my second derivative test. So A is the second order derivative of f with respect to x, which turns out to be 2. And now this is a value of a at any point x comma y. Yeah? Just remember that. It turns out to be constant. It turns out to be constant. Okay. B is the mixed derivative, dou square f, dou x, dou y. Okay. And if I take it as dou by dou x of dou f by dou y is x plus 2y minus 6. So if I put that over here, the value of B is 1 at any point x comma y. Similarly, C, which is dou square f by dou y square, turns out to be 2. And what I see is the value of ABC is constant. So these are the values of ABC at any point x comma y, particularly when it is so if I'm looking at AC minus B square, it is 3. And A is positive. This holds true for any x comma y belong to R. But my second derivative test decides the behavior of a stationary point. So I will take my stationary point. So particularly when my x comma y is a stationary point -3, 2, I get AC minus B square equal to 3 and A is equal to 2. And when this behavior is executed, the point becomes a point of local minima. Okay. So that is how you can check your second derivative test. Now, this is an example what I had seen in your JAM examination paper. You can try checking out this. Don't worry about this condition. This is harmless condition. Okay. You will understand the important. It is what it is saying is, see, you have a sin x function, no? So when you will take a total partial derivative dou f by dou x, okay, and when you will equate it to 0, so you will have to have the value of x which will be in this interval 0 to 2 pi. You can avoid those infinitely many images. Okay, so that way you will have finitely many stationary points. So just to get finitely many stationary points, this condition is inserted. It is absolutely harmless condition. Try doing this on your own. Okay, now answering to the question which was asked by one of your friends, if the function is different, f of x is differentiable, fx and fy need not imply the continuity of f of x and the differentiability of the function does not imply the continuity of the partial derivative. Okay, so here is an example, and you have one very beautiful example in the JAM paper which I have shared after this example. So I have f of x comma y. So this is only the counter example. I am done with my main topic. I'm just doing this counter example, and before concluding, I have to just insert one more topic. I will just touch and go. I will not do that in detail. So I have f of x comma y given by x square plus y square into sine of 1 upon under root x square plus y square if x and y are non-zero, and 0 if x and y are 0. So now here in this case, I want to check the differentiability at the point 0, 0. My aim is prove f of x comma y is differentiable at 0, 0, but fx and fy are not continuous at 0, 0. Okay. So let us calculate this example will help me to see the picture of what is my total derivative, how my total derivative appears also. Okay. So maybe I'll stop my pen and use the thing. So dou f by dou x at 0, 0, by definition it is limit h going to 0, f of h, 0 minus f of 0, 0 upon h. You put the value of h, 0. This will be h square into sine 1 by h upon h. You can cancel out h, and in my beginning of the lecture, I had mentioned that the value of this limit is 0. So dou f by dou x turns out to be 0. Now you try for dou f by dou y. Instead of 0, h, you will have 0, k. So here you will have k square into sine 1 by k divided by k. Again, that will turn out to be 0. So what I see is the partial derivative turns out to be 0. I had defined my t of hk as gradient of f at 0, 0 dotted with the vector h, k. That turns out to be 0. And this is the linear transformation. Now we'll check whether this linear transformation is the total derivative of the function. To check whether it is a total derivative of the function, it has to satisfy the definition. Here it has to get me this particular limit is equal to 0. Okay, let us recall what you have done. So we have seen that a function f. Now a function f is differentiable at a point A. Okay, I'm talking about a function from R2 only. Let us not complicate the situation. Is differentiable at x equal to A. If you are able to find a linear transform T from R2 to R such that limit h going to 0. Now this h is nothing but h comma k. Okay, limit h. Let me not write h comma k. It will confuse me later. So limit h going to 0, f of a plus h minus f of a minus t of h divided by norm of h, modulus of this. If this is equal to 0, then t of h is defined as a total derivative. Okay. Now t is a linear transform. So I hope you remember what I had said. This t is nothing but df at a, and it's a matrix. So in 2 by 2 case, it is dou f by dou x at a into dou f by dou f by dou y at a. Okay. So if this substituted here, so if I'm talking about t of h, so it will be df at a times f. If I put this value over here, and if this gives me the limit 0, then I can say the function is differentiable and this becomes a limit. So that is what we are going to do over here. Okay, this is my f of a plus h minus f of 0 comma 0 thk. Substitute the value of thk is 0. F of 0 comma 0 is 0. I have substituted. This is if I simplify this, if I simplify this, okay, this is precisely f of h comma k. And then if I substitute f of h comma k in the formula of the function, which is seen here. Okay, it is equally s square plus k square into sine. Okay, and then you have limit h going to 0 under s square plus k square into sine of 1 upon under root s square plus k square. If you want, for your convenience, you can take r is equal to under root h square plus k square. So as k goes to 0, r also goes to 0. And this will simply turn out to be, this portion will simply turn out to be r into sine 1 by r. And this limit is 0, we have already proved. So the function is differentiable at 0, 0. But you can check on your own if I'm talking about the partial derivatives here. Okay, if I'm looking at dou f by dou x, you can take a partial derivative here by applying u to v formula and all the other formula. It will turn out to be this function. Particularly when y is equal to 0, it is 2x into sine 1 upon mod x minus x upon mod x into cos 1 by mod x. So now, if I'm allowing x to go to 0, okay, this is not a problem. This will go to 0. Okay, whereas this is not defined. Okay, this limit will not exist. So my limit of dou f by dou x at x approaching 0, this does not exist, and hence my the derivative of f with respect to x is not continuous. Is not continuous at 0, 0. Similarly, you can take dou f by dou y is not continuous. There's something called the concept of constraint maxima. I think the time is almost over. I have exceeded the time, but you can read that on your own. You have some very nice questions about like finding a maxima of a function if I'm taking a point on the curve, on this particular curve. And it's a very simple topic. So that is one question what you should try. I could not include that over here. And there are 2-3 questions in the sheet what I have downloaded. I will share that with you. But I think after this session, you should be able to do it confidently. Okay, that's it from my side.
Okay.
So thank you for giving
Okay,
the
thank you,
opportunity.
Dipali.
Yeah, I hope this will be useful for students those who attended.
Of course, you have explained the concepts with a lot of examples and nice problems. Okay, now it is the time for feedback. So, dear participants, you may please share your feedback.
Hi, ma'am. I'm Adira. I'm from Government Victoria College, Palakkad. Actually, it was a wonderful class. You explained many concepts very well, and it was easy to understand. Thank you, ma'am. Looking forward for more classes.
Yeah, thank you, Arira. I just hope you find it useful. Just make best use of it.
Yes, ma'am. It was very useful. Thank you so much.
Thank you.
Yes, others.
Hi, ma'am. I'm Parvati from St. Teresa's College, Kerala. The session was really good. The way you explained was really nice. After explaining each concept, you solved the problems, which was very helpful. Thank you, ma'am, for your valuable session. And thank you, Vinod sir, for organizing such a wonderful session. Thank you.
I'm Soumya from MI College, Kerala. The way you explained the concept was amazing. It was simple to understand, and the way you explained each problem related to the topic was very helpful. Thank you so much, ma'am. And thank you, Vinod sir, for organizing the class.
Thank you,
Thank
Soumya.
you.
Hello, ma'am. I'm Aditya Krishna from Government Victoria College, Palakkad. Your session was very useful and very helpful and very informative. Thank you, ma'am, for being part of this session.
Thank you.
Okay, thank you, Aditya.
Hello.
Okay, thank you, Sharada.
Thank you.
And thank you, Vinod
Yes.
sir, for organizing
Yeah,
such a wonderful
Dharmendra Singh
session.
has a doubt. Yes.
Yeah, yes, Dharmendra.
Yeah.
Okay, thank you, Sharada. Yes, Dharmendra.
Excuse me. Sorry. Session was very nice and problem also very nice and some problem are very good problem and easy problem. And I want to ask about which book should we follow for several variable function problem. And I want to ask about experience of research of Ma'am Dipali. Thank you, sir.
My
Thank you, ma'am.
experience, research experience, Dharmendra sir, I do not have that big research experience. I'm still working on some of my research work. So there is not much to share. I think Vinod sir will be the correct person to guide you when it comes to research. I'm not a person who is mainly a researcher. I enjoy being a teacher rather than a researcher. And the book, you can refer to a calculus book. Whatever I have collected right now, it is from my lecture notes only, which I have made by using referring to the different books. So one book will not be sufficient, but I think Apostol could be the one, or otherwise you have to, I mean, if you open the calculus syllabus, which is listed on the UGC website, you will find the number of books on calculus. Sometimes I search, Google search, if I get a good book, if I get a good example, I just download from there and use it in my class.
Thank you, ma'am. Thank you, sir.
Okay. Thank you, Dharmendra. Let me add some point about Dipali. She qualified UGC NET JRF with all India rank 81 and did her MPhil from University of Mumbai. And she is serving as a assistant professor in a GN Khalsa college.
As I said,
doing,
I'm not
I
a
think,
researcher
PhD
kind
in
of
part-time
person.
basis, I think. It's okay. Anyway, you are really nice
I'm not a
teacher.
research kind of
Explain
person.
the
As I said,
things
I
in a
like to
very
be a
well
teacher than a
manner,
researcher.
which are understandable for any student who are seriously watching. Okay. Thank you, Dharmendra. Any others?
Thanks, sir. Thank you, ma'am.
Yeah.
Hi, ma'am. I'm Aishwarya from Assumption College, Varanasi. The session was very good. You made the concepts clear and the problems you discussed made it more easier. Thank you, ma'am, for the session, and thank you, Vinod sir, for organizing the session.
Okay, thank you, Aishwarya. Any others?
Hello, ma'am.
Yes.
Yeah.
Ma'am, the session was nice. Despite the technical glitches and all, you managed to pull off a great session.
Thank you. The session was a bit fast-paced for me because I am just beginning to learn multivariable calculus, but your explanation made it seem very simple and easy. So thank you for the great session.
In which year you are? First year, second year, or maybe
Second year.
second year? Huh? So you are yet to do little more of calculus. Once you do that, you will understand because the course must be the ongoing course for you.
Yes.
Yeah, Praveen is now second year, but he is very active and he has attended the MTTS camp, online foundation course and all that. So certainly he will catch up the things. I'm sure that.
Yeah.
Yes. Thank you, Praveen. Any others? If any of you, yeah.
Hi, ma'am.
Hi, ma'am.
Yes.
I'm Gobika from St. Thomas College, Thrissur. As Praveen already stated, I'm also in second year. So I too felt a little difficulty in following. But I think it was really nice and ma'am made me feel like the topics were easy. So I thank ma'am for the valuable class. I also thank Vinod sir for organizing this class. Thank you.
Thank you,
Thank you,
Gopika.
Gopika.
Yes, Lakshmi.
Good afternoon, ma'am. My name is Lakshmi. I'm currently final year student at Hansraj College. Thank you so much for the session, ma'am. MVC has always been one of the tricky subjects for me. So thank you so much for putting it out so clearly. Thank you so much.
Thank you.
Thank you, Lakshmi.
Good
Yes.
afternoon, ma'am. I am
Yes.
𝕊𝕚𝕚𝕚𝕒 from St. Peter's College, Kolancheri. Today's section was very interesting. Thank you, ma'am, for your wonderful lectures and discussion. And I have learned a lot from it. Thank you, Vinod sir, for arranging this class. Thank you.
Thank you, Elsa.
Thank you.
If any of you would like to share a feedback, please. So I think it's over. So anyway, would like to thank you, Dipali, for being with us. This is the second time you are with us for engaging such a session. And
Thank you.
don't forget to inform your students about our group and ask them to join with us.
One of my students was attending, Arjana Singh. I don't know whether it disconnected. And one or two more students from my college, I have recommended them. Those who are interested particularly in doing the research. Some of them are very small, like some are in first year or second year. So I thought I'll tell them after they reach third year.
Yeah. Okay, once again, I would like to thank you on behalf of our Maths Aspirants community for being with us. Thank you, Dipali. Please share your notes as a PDF so that we can share it with in our group. May be useful for the participants.
Yeah, sure, I'll share. I'm just sorry for the inconvenience caused in the beginning. There is some work going on in my area, so I had to connect from mobile data. I never expected this kind of situation will arise.
Yeah,
So
it's okay. For an online session, this type of hurdles will always be there. We have to expect this type of issues. But anyway, I think it has gone in a with not much problems. Even though your mobile network it was good. The session gone in a very well manner. Okay. So thank you. Let us wind up here. Thank you.
Thank you.
Thank
so
you,
much.
everyone.
Thanks.
Bye.
Bye.